There's a sound you know without having to think about it. A sound so ordinary that your brain stopped registering it years ago. The way you stop hearing a clock tick in a room you've been sitting in long enough. It's the sound of an engine turning over. That particular mechanical rhythm. That brief shudder before the idle settles. That small explosion happening dozens of times per second. Somewhere under the hood of a car you probably drove today. Or sat in yesterday. Or will borrow tomorrow. You don't think about it. You've never had to. The car starts, the car moves, the world continues, and somewhere in that assumption, in that not thinking, is exactly where this story lives. Because the reason that engine doesn't knock, the reason it doesn't rattle itself apart under load, the reason you can press the accelerator on a highway on-ramp without the whole mechanical system fighting against itself, that reason has a history. And that history begins with a rock. Not a metaphorical rock, a real one. Dense, gray-blue, soft enough to scratch with a fingernail. The kind of rock that civilizations have been pulling out of the ground for thousands of years because it melts easily, because it forms into shapes, because it's everywhere, and because for most of human history, the fact that it was quietly doing something to the bodies and minds of everyone who touched it was either unknown, ignored, or explained away as something else entirely. The Romans used it to sweeten wine. Painters ground it into pigment. Plumbers shaped it into pipes. The very word plumbing comes from the Latin for lead, plumbum. For centuries, this material sat at the center of human civilization, not despite being toxic, but completely indifferent to the question. And then, in the early 1920s, a chemist named Thomas Midgley Jr. did something that seemed, at the time, like one of the most useful things a person had ever done with a piece of chemistry. He solved a problem. The problem was this. The new internal combustion engines being built for automobiles were knocking. When the fuel-air mixture in a cylinder ignites prematurely, before the piston is in the right position, the engine makes a sharp, metallic sound. More importantly, it loses efficiency. It wears itself down. Engineers were searching for something, anything, that could be added to gasoline to make it burn more smoothly, more controllably, more in time with what the engine actually needed. They tried dozens of compounds. Most of them didn't work. Some worked a little. And then Midgley tried a small quantity of tetraethyl lead, a compound made ultimately from that same ancient gray rock. And the knock disappeared. The engine ran clean. The engine ran smooth. The numbers were extraordinary. The improvement was not marginal. It was the kind of result that makes a researcher want to check the equipment, recalculate, check again, and then, when everything keeps pointing to the same conclusion, begin to feel that rare and specific excitement that comes from being first. This is the moment the story could have gone differently. This is the moment where the small flaw was already present, already visible to anyone looking for it. But the looking wasn't happening because something much larger was happening instead. Something that feels in retrospect almost inevitable. Because the problem that had been solved was real. The solution that had been found worked. And when something works, when something solves a genuine, expensive, frustrating problem in an industry that is moving very fast and has a great deal of money behind it, the questions that might otherwise be asked tend to get quieter. Midgley himself apparently developed lead poisoning during his research. He took a leave of absence to recover. He came back and continued. The workers at the first commercial production plants died. Not slowly, not ambiguously. They died in ways that were obvious enough to generate newspaper coverage. They called the facility the House of Butterflies, because of the hallucinations workers reported before the end. Standard Oil acknowledged the deaths. The response, more or less officially, was that more research was needed. Tetrethyl lead went into production anyway, and here's where the story stops being about one chemist, or one company, or even one era, because what happened next happened slowly, over decades, across continents, into the lungs and bloodstreams of hundreds of millions of people who had no idea it was occurring. Leaded gasoline burned in engines across the industrialized world, and the exhaust that came out of those engines contained fine particles of lead, and those particles went into the air, and the air went into everything. Into soil, into water, into food, into children, into the developing nervous systems of multiple generations of human beings growing up in cities where the concentration of atmospheric lead was, by the time researchers started measuring carefully, elevated by factors that were difficult to comprehend. The research, when it came from a geochemist named Claire Patterson. He wasn't looking for this. He was trying to measure the age of the Earth using isotopic ratios and ancient meteorites. And to do that, he needed extremely precise measurements of lead concentrations in rock samples. And he kept getting contaminated results. The lead was everywhere, in his samples, in his laboratory, in the air itself. It took him years to build a clean room capable of producing uncontaminated data. And in doing so, he realized that the contamination wasn't coming from somewhere unusual. It was coming from everywhere. The entire atmosphere of the planet had been steadily accumulating lead since the 1920s. Patterson published, "The lead industry funded counter-research." He was removed from advisory committees. His funding was threatened. He continued anyway. The argument he made was not complicated. The concentration of lead in the blood of modern humans was roughly 1,000 times higher than it had been in pre-industrial populations. This was not natural variation. This was not within the range of anything the human body had evolved to handle. This was a civilization-scale experiment being conducted on an entire species without consent. The phase-out of leaded gasoline in the United States took until the 1980s. In some parts of the world, it continued into the 2000s. The neurological effects on the generations exposed during peak years of use, the measurable, statistically significant effects on IQ, on impulse control, on outcomes across enormous population studies, those are documented now in the careful language of epidemiology, which means they are also, in some sense, closed. The numbers exist. The harm is not really in dispute, but it doesn't feel like anything when you read it. It doesn't feel like a conclusion. It feels like something you're being told happened to other people in other times, and it sits at a distance that is hard to close. And it was here, somewhere around this distance, that Richard Feynman's particular kind of thinking becomes relevant. Not because Feynman had anything to say about lead specifically. He didn't, as far as the record shows. But because the way Feynman thought about materials, about solutions, about the relationship between a thing that works and a thing that is understood, that way of thinking describes exactly the failure mode that made all of this possible. Feynman was suspicious of what he sometimes called cargo cult science, the performance of rigor without its substance, the adoption of a result without the understanding of a mechanism, the celebration of a thing that works without the harder, slower, less rewarding work of asking why it works and what else it might be doing while it's working. He didn't trust elegance for its own sake. He didn't trust convenience. He was famously uncomfortable with the way institutions and industries and even scientific communities could develop a shared interest in a conclusion and then stop examining it. not through dishonesty exactly, but through the slow accumulation of not asking. The problem with tetraethyl lead was never that nobody knew lead was toxic. They knew. The problem was that the toxicity had already been established in a different context: occupational exposure, direct contact, acute poisoning. And the assumption was made, without being tested, that low-level atmospheric exposure was a different category of problem, that the dose made it safe, that the mechanism of harm in one situation didn't transfer to another. This assumption was wrong. It was wrong in a way that was knowable at the time, with the tools available at the time, if the question had been asked in the right way. But the question had a cost. The answer had a cost. And the material worked. This is not a story about evil. That's part of what makes it hard to sit with. The engineers who needed better fuel weren't wrong about needing it. The chemists who found a solution weren't inventing a problem. The companies that scaled it weren't doing something unprecedented in the history of industry. Every single step, taken individually, made a kind of sense. The logic held at each junction. The error wasn't in any single decision. The error was in the structure of the thinking, in the implicit belief that a solution that solves the problem you can see is a solution that doesn't create problems you're not looking for. Feynman, in a different context, talking about something else entirely, described what he considered the first principle of scientific integrity as not fooling yourself, and noting that you are the easiest person to fool. The mechanism he was describing was not incompetence. It was something more fundamental. It was the way the mind, once it has found an answer that works, naturally stops generating the next question. The way success is its own kind of cognitive closure. The way a material that solves your problem becomes, in a very quiet and involuntary way, a material you've decided is safe. Not because you've tested it, but because you've stopped thinking of testing it as something that still needs to happen. What's strange is that this dynamic is not historical. It doesn't belong to the 1920s. It's not a feature of a less scientifically sophisticated time. The same structure, a material that solves a pressing problem, adopted at scale with the harder questions about long-term and systemic effects deferred in favor of the immediate and measurable results. That structure keeps reappearing, and not because the people involved are foolish, but because the incentive to ask the next question is always weaker than the relief of having found an answer to the last one. Patterson spent years of his career fighting for results that nobody in a position of institutional power wanted to be true. He was not, by most accounts, a particularly political person. He was a geochemist who followed his measurements. The measurements kept pointing somewhere inconvenient, and he followed them there anyway. And the resistance he encountered was not primarily about the data. It was about what the data meant for people who had built large structures of commerce and assumption around the thing the data was describing. The data won, eventually. It usually does, eventually. The question is always just how long eventually takes. And what accumulates in the meantime. The lead is still there, by the way, in the soil, in sediment layers that researchers can date with precision, watching the concentration rise through the middle decades of the 20th century and then slowly, partially fall. In the bones of people who were children in the 1960s, where it will remain for the rest of their lives. Patterson's work established that there is a pre-industrial baseline for human lead exposure, and that we departed from it, and that departure has not been fully undone. You cannot remove it from the record. It's part of the stratigraphy now. A thin layer of human decision-making preserved in the geology of a planet, the way all the large, slow decisions eventually are. And here is where the story does something that most stories of this kind don't quite manage. Because it doesn't end with the phase out. It doesn't end with the vindication. It ends with a question that doesn't have a clean answer yet. And it ends there specifically because pretending otherwise would be the same kind of not asking that made the original problem possible. The question is about what we are doing right now that looks from inside the logic of the present moment, exactly the way leaded gasoline looked from inside the logic of 1923. The question isn't rhetorical. It's not a gesture toward some vague future accountability. It's methodological. Feynman's first principle, not fooling yourself, doesn't come with a list of applications. It doesn't tell you which current material, which current solution, which current convenience carries within it the next version of this story. It just tells you that the fooling is most effective precisely when everything is working, when the answer has been found, when the problem has been solved, when there is the least apparent reason to keep asking. The engine you drove in today runs quietly. It doesn't knock. It doesn't rattle. It performs exactly as designed. And somewhere in the infrastructure of that smoothness, in the generations of engineering decisions, chemical discoveries, and industrial scaling that produce the specific, reliable, ordinary machine that starts when you turn the key, there are things that worked, and things that were understood, and things that were assumed without quite being tested, and things that were known and deferred, and things that are not yet known at all. These categories are not always clearly separated. Sometimes they were separated and then allowed to blur. Sometimes the blurring was an accident. Sometimes it was more deliberate than that, and the records of those deliberations exist, and they are not comfortable to read. The rock is still soft, still gray-blue, still easy to scratch with a fingernail, still everywhere underground, and in some places still being extracted, still being used, still being found in paint and old housing stock, still present in water systems in cities that haven't finished replacing the pipes that were chosen because of the same properties that made it useful for everything else. The geology hasn't changed. The chemistry hasn't changed. What changed, slowly and incompletely, and not without resistance, was the question being asked about it. That's the whole story. That's all there is. A material that worked. A question that was deferred, and a geochemist who followed his measurements somewhere nobody wanted him to go, and arrived at a number that rewrote what it means to be a human being living at the particular point in history when something very old was briefly treated as something new. The next time you hear an engine idle, that small, controlled, repeated combustion settling into its rhythm, you are, without knowing it, at the end of a very long chain of decisions about what questions are worth asking and when. Most of those decisions were made before you were born. Some of them were made correctly. The ones that weren't are still in the soil.